Thanks. Thank you very much for the introduction. Good morning, everyone, or good evening in Russia. Uh, Today, my talk will be about computer vision and machine learning with OpenVX. I'm currently the staff engineer at AMD and the OpenVX chair for the Chronos group. So today's agenda, we'll just go over OpenVX, what it is and what the overview is. And then we'll talk about the latest OpenVX, which is OpenVX 1.3 highlights and new features. We'll talk about what are the few common questions that people have about OpenVX. And then we'll see what a conformant OpenVX is. And then we'll see some sample implementations and see what OpenVX for Raspberry Pi looks like. Those of you who are enthusiastic about doing small whole projects, OpenVX is available on Raspberry Pi. And then we'll take a deep dive into OpenVX cross-platform application case study, where we'll take an open source application, run it across, and then see how it performs. And then in the end, we'll give some conclusions to this open standard and open up the floor for live questioning. All right, most of you might be familiar with what OpenVX is, but if you're not, OpenVX is an open royalty-free API standard for cross-platform acceleration in computer vision applications. So when I say it's an open royalty-free API, so API is completely different from open source libraries. So what is an API is like the first question, right? So not going into the Wikipedia definition, application programming interface, you can think of it as a messenger, right? So you give your request, the messenger takes your request, goes to a library, database, or an application, and brings back your data or your response. So simply put, an API is just a messenger. So if you want to add an analogy to it, think of it like an waiter. So you go to a restaurant, you have menu of items. So it's similar to an API spec. So API has a menu of items. So you choose what you want in the menu and you say to your waiter, okay, I need this. The waiter goes in to the kitchen staff and brings out your meal. So the better the waiter understands what you want, the better your meal is going to be. Like if you have certain preferences, you want certain spices to be taken out, or you want certain cooking method. So if the waiter understands you, that means the API did its job, right? So in computer world, similarly, an API needs to understand the developer's needs. So the developer needs to say that, okay, I need this image output, or I need a slight variation to my output. So he needs to take the response and go to this database or an application or any kind of library and bring you back your right response. So with that in mind, APIs need to be designed for the developer, right? So the API is a real world thing. So why are APIs important? Why am I stressing that APIs are important? So APIs act like the building blocks for any application. So most of you are familiar with booking air tickets. I mean, now it's Corona time, nobody is booking anywhere. But in general, when you're booking air tickets, it's an API which goes to a bunch of different airlines and brings the data you require, like, oh, okay, what time, where do I need to fly? So depending on the API, acts as this building block which lets people create your own application. So imagine if you had to build everything from scratch, you would never complete an application. So a good API acts like a good Lego block. It fits right in your application, gives what you need, and it works well. So obviously, if this happens, it speeds up your development. So you're not spending time in developing libraries or applications that you're not familiar with. So you're leaving those to the experts who are working on it for years. And then you're using their work in your application. So you're getting the best of both worlds. And then the other important thing about this is portability. So let's imagine you're writing an application and it only runs on Windows, right? So every time you want to run it on Mac or you want to run it on Linux, if you have to port it, if you have to spend all this time working and trying to get your application to work on another platform, that's time consuming. That's time taken away from time you could spend on your application. So you need to think that portability is an important issue across different OSs, different platforms. So you want to future-proof your application as a developer. And then finally, innovation, right? So innovation is obvious because if you don't spend much time on things that you don't need to, if your development is speed, and if it's portable, then you're spending more time on your application. You're spending more time on your computer vision or machine learning application. You're working on the top layer and you're getting your work done. So with that in mind, OpenVX enables portable, uh, performance portable, and power optimized computer vision processing across OSs and across platforms, and which is kind of very important these days in embedded and real-time applications. So OpenVX is the only vision API shipped as an optimized driver. So we'll talk about that in a couple of slides in the future. So over here, you can see this block diagram where you can see the lowest layer is your processing hardware, which could be anything, x86 processor, dedicated vision processor, DSPs, accelerators, GPUs, any of those, right? So what you as an application developer needs to be shielded from what your application is. So if you are trying to, like I said, worrying about, oh, will it run this on this hardware? Will it get me the best optimization? Then you're not working as an application developer. You're spending more time on things that doesn't concern you. So OpenVX lies in between this layer where it acts as an engine or a framework and gives you that powerful, flexible API to actually access this hardware and get you the best performance. So OpenVX underneath is written sometimes in C++ to run on like sample implementation or SSE or AVX12 code or OpenCL to get maximum performance out of a GPU, or sometimes even an assembly language, depending on the implementation. So with that in mind, you saw that in the previous diagram, OpenVX also lived in the layer of framework. So what framework does is it gives you the graph structure. So you have OpenVX nodes, which do individual operations. Like let's say you're doing add or subtract, something like that, real simple. And if you need to call them a bunch of times or do a couple different kind of operations on an image, the OpenVX runs them as a graph. So it has a graph structure. So it builds a graph. So what this graph does, it gives you optimizations. So when I say optimizations, so a given application, you know what the nodes need to go for your application. Let's say you're doing something like a K-NY edge detect. So you have K-NY nodes or like a dilate and erode, or you have some kind of background subtract, something like that. So you know what your application has in all its layers. So the graph optimizer looks at the whole layer and sees, okay, what nodes can I merge? What nodes can I fuse and get the best performance out of it? So these kind of optimizations are in the graph optimizer. And it gives you overall better performance. And we'll look at that, how it does in the future slides. And then the other thing is the memory footprint, right? So if your application needs a gobs of memory and it takes up all the space, it cannot run in embedded space. Embedded is already space crunched and you have less memory and your application is fighting with a bunch of applications to get like resources. So you want to use as less resources as possible and give the best performance. So the graph optimizer looks at your graph and sees, okay, where can I use or reuse these memory objects over time? Because if you have an output A and output B, and if you're not using output A after you produce it, you can reuse that memory again for output C or something like that. So these kind of optimizations are added into the framework. So when you as a developer call the API, you don't have to worry about it. These are all given to you at free of cost, right? Like it just comes to you as a benefit of using a good API. And the third one is deployment. So when you want to deploy a computer vision or machine learning application, you want to see that is my application supported across CPUs, ASICs, discrete GPUs, and OpenVX with a bunch of implementations. I'll show you in the future slides. It has diverse range of computer hardware that you can use right now. So with that, we just released OpenVX 1.3 in terms of time. It was like a year ago, but with Corona, we have forgotten the concept of time nowadays. So OpenVX 1.3 was released October 22nd, 2019. So the main reason we released OpenVX 1.3 was to give developers or the adopters the deployment flexibility and avoid fragmentation. So what I mean by that is as an API grows, right, as an API or any library grows, there you add more and more functionality to it. So what it does, it changes perspective of adopters. So let's say you're an adopter who's only interested in machine learning, and you have to implement OpenVX. So let me be clear with what an adopter and a developer is. So an adopter is someone like AMD, right? And AMD is a chip manufacturer. So we know what our hardware is. So we adopt OpenVX, we develop OpenVX, and we give it free of cost to the developer, right? A developer who's using AMD chips can use AMD's OpenVX and run their application. So that's the difference between an adopter and a developer. So what happens is if I'm a company, for example, let's say if I'm a company who's only interested in machine learning, I don't want to do any of those computer vision applications. So OpenVX doesn't want to force everybody to implement all the nodes. So what we did is we created feature sets. What these feature sets means is you have a bunch of functions which are similar in kind, and they're all grouped together so that if you are an adopter, you can implement one or two of these feature sets and be fully conformant. And because of this, now you have diverse implementations to run your application in. So what are these feature sets, right? So we talked about all these feature sets to be unifying a bunch of functions. So with OpenVX 1.3, we have the graph infrastructure, which, like I talked about, is a baseline framework. And this is a compulsory feature set, which all the adopters have to implement. And then you have the vision, which is the core vision functionality. And then you have enhanced vision, which is functions added in OpenVX 1.3. And then you have the neural net inferencing, which includes tensors, object, and others. And then you have NNEF import. So most of you who don't know what NNEF is NNEF is another file format, which is neural net exchange format. So where you do your training in TensorFlow or PyTorch or Caffe, and then once you're done training, you have your trained model, and you want to represent this trained model in a very simple way so that your application understands it. So that's where these Onyx and NNEF come to. So Onyx is another open source implementation of this file format, and NNEF is a standard from file format from Chronos group. And then you have the binary image, and then you have safety critical for reduced feature set and enhanced safety certification. So that's for more like if people are using OpenVX in automation or in safety critical, like a car. So if you're doing some kind of inferencing computer vision on a car, you want to be safety certified. And that's the feature set you will be looking for. Now with that, let's see what usually people have some misconceptions about OpenVX, and they get confused with what OpenVX can and cannot do. So let's clear up some of those misconceptions or common questions that people usually ask. So the first one is OpenVX an open source library? So like we talked about in the previous slides, OpenVX is not a library. It's an API defined by the OpenVX working group, where anybody is free to implement a library from it. So the API is defined by the working group. Working group basically consists of a consortium of all industry members. That's what Chronos does. It's a nonprofit standards body, and we create a bunch of open standards. And you might have heard about Vulkan, which I think will be talked about in the conference. You might have heard about OpenCL. You might have heard about OpenGL. So all these good standards are from the Chronos group. So these are defined by the Chronos group, and anybody like AMD or Intel or NVIDIA can implement this and provide it to their developers. So the second one is must I pay royalties and licensing fees for using OpenVX, right? So again, there is no fees or there's no royalties involved. So if you're using OpenVX on a conformant implementation, you're also protected by the Chronos IP framework, which means that you have a better application with no royalties. So if you use this in your production code, so you don't have to worry about some lawyer suing you that you're using their IP. So you are protected with the licensing and royalties. So the other one was usually people ask is, oh, should I be a Chronos member in the consortium to use this? So not true at all. Chronos members and non-members can develop conformant implementations, and it can be used by all. So it can be used by students, professionals, or like companies. As long as you're using a conformant implementation, you're protected by the Chronos IP framework. The other thing people think is, okay, I know that OpenVX is good, but aren't the number of functions limiting? Like if you compare OpenVX to OpenCV, which is another great open source project, which has a whole bunch of applications or a whole bunch of computer vision and machine learning nodes, isn't it limiting to have OpenVX, which has these feature sets and limited? So like I mentioned, the working group wanted to have a tight focus on computer vision application, machine learning application. So the goal was not to have every function out there in the spec, right? You need to have a tight focus on what is the industry want, what do customers want, and have those functions well designed rather than having 10,000 of things which people wouldn't use. So the OpenVX was more tight focused. And if you need another node or if you need something which is not there in the API, you can always extend with custom extensions. You can write simple custom nodes where OpenVX allows it. And it also gives developers and vendors options to create new OpenVX extensions. And I'll talk about it in the next topic. And the only thing here is when you implement your own node with OpenVX, this particular module will not be portable. So that means that if you're running, let's say on an x86 platform, and you create a custom node and you want to move it to ARM, so the only part which is not portable will be the custom node that you wrote for x86. So you have to rewrite that part in the ARM spec. So the other question is, are implementations different? So does it mean that an implementer A versus an implementation B, if I use two different platforms, will my application run the same and produce the same output? And that's a resounding yes, because OpenVX has this testing called the conformance test suite, where anybody who has implemented OpenVX and has given the conformance needs to run this thousands of tests to make sure that every output and every node is tested and it performs and behaves the same way. So like I was mentioning, so popular vendor extensions get adopted as Chronos extensions for future testing with conformance. So what are these OpenVX conformant implementation that I keep talking about? So when I say conformant implementation, they must pass the exhaustive conformance test suite, which has thousands of test cases, and they have to pass all these to make sure that the implementation is doing what it says. So when a developer uses this API, he's getting the right answers every time. And then these are the hardware vendors who have all submitted a conformance with OpenVX. So you can see all the major chip manufacturing companies, AMD, Intel, NVIDIA, Synopsys, everybody has their implementation. So with that, what we did as a working group is we created a sample implementation of OpenVX and made it open source on GitHub. So the whole open source concept is taken over. So we thought it would be best to give developers a sample implementation. We implemented the whole OpenVX spec and put it out on GitHub so that anybody can use it. So the purpose of this software is not to create like an optimized production ready sample, right? This one is more of a sample implementation, not a reference implementation. So when I say a reference implementation supersedes a given spec. So this is just a sample implementation. So what this does is it's passing OpenVX 1.3 conformance. So let's say you want to run this on an x86 platform. So you can use this open source implementation and test and develop and do some kind of prototyping. But if you want to use this OpenVX in your production, you're going to use the optimized OpenVX libraries from the vendors. So maybe Intel, maybe AMD. So whoever it is, you're going to be using their optimized OpenVX. So the next topic is OpenVX for Raspberry Pi. So the Chronos group and Raspberry Pi Foundation actually worked together, and we implemented an open source implementation of OpenVX 1.3, and we pushed it out for everybody to use on Raspberry Pi. And like I said, with 1.3, we have these feature sets that needs to be passing. So currently we are passing vision, enhanced vision, neural net, and NNEF kernel import conformance. And this implementation is neon optimized, and it's available for everybody to use. So like I said, if you are somebody who is an enthusiast who want to do some kind of home project, this is great. So you can download the OpenVX for Raspberry Pi and develop your own computer vision machine learning application, and then you can still get the performance. And if you want to tweak or add some nodes, you're free to do, and you're free to contribute to the community in general. So with that, the conformant hardware for this is Raspberry Pi 3 and Raspberry Pi 4. And I have listed all these information in the resource slide, and we'll look at it in the end. And this was the response with OpenVX for Raspberry Pi. So the chief executive of Raspberry Pi, Ebden, he was really happy. He gave us a quote on, and this is right now on our OpenVX website. He was very happy to get Raspberry Pi and OpenVX together, and he's happy that all his guys can get a computer vision application with an API which is well built for creating applications. And here OpenVX was also highlighted on their website. So I just screenshotted that for you guys. So if you want to read more about the blog and the whole, it's available on the Raspberry Pi website too. All right, so the next one I wanted to briefly discuss was the NNEF import conformance feature set, right? So this one kind of an important feature set where you are trying to do machine learning and you want to do on a given platform. And I'll explain how people are going about these days. So let's say you're doing some kind of training and you're going to use TensorFlow or PyTorch or Caffe or whatever framework you're comfortable with. So once you're done training and you have a model which you think you can deploy it, so the work doesn't end there. So now you don't want to use a real bulky framework on something like a Raspberry Pi. So you want to get rid of all the bulky framework aspects of that model and just run the core compute and get the best performance on your inference. So what you're going to do is you're going to translate that pre-trained model, which is in any of those format, to an open source open file format, which is like an NNEF or ONNX, whichever you're comfortable with. So NNEF is neural net exchange format. It's by the Chronos group. More information is on the Chronos website. I won't go into that because it'll just go on a tangent. So you would convert your model into an NNEF model, and then you would import this model into an OpenVX graph, and then you're going to run your neural net with computer vision. So what I mean is when you run a neural net or an inference application, you're not just running the inference. You're going to grab an image from a camera source or a file or something from an internet, if you're using an IP image for your application, depending on whatever your application you're doing. you're going to do some kind of pre-processing. So you're going to resize, or you're going to filter, or you're going to sharpen the image. So there's some kind of computer vision involved in the beginning. And then you're going to run your inference. And then once your inference is done, you're going to post-process this output. So you're going to need some kind of computer vision. So if you see, if you build an OpenVX graph end to end, you have this tight, streamlined build of a graph, which is tightly integrated. So you don't have to move your data from one format to another. Everything is neatly packed in a one graph, and then you're running this whole thing on an optimized API. So that's how it works. So you have this one node which imports your whole neural net, runs it for you, and then you get your output. And the sample implementation is currently available on GitHub. So those of you who are interested to trying it out, please feel free to go ahead and download it. And with that, let's go into a case study today, right? So let's look at what OpenVX cross-platform application looks like. So what we did as a working group is we created an open source samples. So we put together a few samples on GitHub where anybody can download any conformant implementations from the internet, build it, and link this application, and then run it. So I'll provide the link in the end of the slides, or I'll make it available so that you guys can download it. So with this project, what I did is I went ahead and took one particular application, which is a skin tone detector. Basically, it just recognizes your hand and your face. And this is a very simple application, and people can build on top of it depending on your use case. So what I did here today, you can see this whole application in this one paper here, and it says, you have an input, you extract, you subtract, you do some thresholding, and then you do some ANDs, and you kind of get the skin tone detector. So here it is. So what I did is I took that application, open sourced application, and built the Raspberry Pi implementation of OpenVX. And I built it, and without changing any code on my sample application, right? So I didn't change anything on my sample application. I was able to build on Raspberry Pi. So Raspberry Pi, mind you, it has an ARM core underneath. So this one, I'm running the skin tone detect on Raspberry Pi 4 using the open source implementation for OpenVX, the Raspberry Pi implementation. And what I did, I took the same code. I did not change anything, though I did not change anything on the sample application, and built AMD's open source MIVisionX, which provides the OpenVX libraries. And I linked the application together. And then here I'm running the same application on Windows on an x86 processor. So again, over here, I did not change any code on my application. So this makes it really easy, right? So you don't have to change anything in your application to run on a given platform. And again, what I did is I took the same application, built it with the open source implementation of the sample implementation for OpenVX libraries, linked the application, and voila, I'm able to run it on Ubuntu right now on an x86 processor. And again, no change in the source code. And here we have me running the same application on Mac, again using open source MIVisionX for OpenVX libraries from AMD. So what this tells is, as an application developer, if you develop an application and you want to distribute across different platforms, different OSs, you can do it without any problem, right? So you saw the list of conformant OpenVX implementers. So if you use any of their platforms, you could just take their implementation underneath and just run your computer vision machine learning apps. And you don't have to do any of those tweaking the libraries and trying to get the performance. Because always remember, if AMD or Intel or NVIDIA is writing the OpenVX libraries, the engineers in their companies know what is the best way to write the software for their hardware. I mean, most of the time, right? There are always instances where you have people external helping with open source libraries. But most of the cases, you can assume that these engineers know what they're doing. So they have given you the best optimization they can get or squeeze out of their hardware. So as a developer, you're not worried about the underneath libraries being optimized. You're more concentrated on your application sphere. With that, so I just downloaded the simple application. So there's some kind of performance. Here on the left, you can see the OpenVX graph unoptimized. And on the right, you can see OpenVX graph optimized. So what I mean is the OpenVX spec allows people to write the graph, right? So you can either write your whole application as a graph, or you could just write it as a serial processing nodes. So where you write node A, node B, node C, node B without the graph context and still run it. So what that does, it does not allow the graph optimizers to look at your whole application and do that optimizations which is built in it. So you can see on the left, the simple application without the optimization base level 1x gives you like 2.54x when compared to just using the graph optimizations by just eliminating or fusing a few nodes here and there. And what about memory footprint, right? So if I don't use the graph optimized implementation, which is the immediate nodes, which is called VXU node that I talked about, there's provisions for that. If you're interested, there's more literature on the OpenVX website, how to do this. And on the right, you can see by simply writing my application in a graph, the graph can look through my nodes and say what memory objects it can reuse. So this kind of saving can be like a huge thing if you're running some small application on a small embedded device or an embedded processor. These kind of savings come very handy when you're trying to get the best performance or squeeze out as much workload you can launch on a given platform. So with that, a few conclusion, right? So the talk was not really geared towards conclusion, but as a software engineer, if I'm developing an application, I always look at, okay, what am I using for APIs on my hardware, right? Like, what am I using inside my application? So that needs to be the first thing you got to think about, is if I'm developing an application, what platforms I want to run, what targets I want to hit, what is the memory or what is the performance constraint. So you want to think about these before you actually go into your project. You want to think where I want to deploy, what is my use case, where am I going to launch it, am I using open source APIs, am I using APIs which in the future, if I make this application a commercial application, do I have to pay royalties? Do I have to pay licensing fees? Will people sue me? So you got to think about these before you start your application. You want to make sure that you use whatever resources you have to make sure that you're getting the best APIs in your application. So as a developer, I always look at what APIs I need to use in my application. And OpenVX fits right in my computer vision and machine learning application, because one, it's optimized, it's portable, it's supported on many platforms and across OSs. So these kind of things are given free to me. So why not use it in my application? Like I said, OpenVX is unique in being the only vision API shipped as optimized driver. So the second point I note is also that OpenVX sometimes is equal to hand optimized non-portable code. So what I mean by it, so people always like say, oh, how does it mean like hand optimized? Because I'm using a library on platform A, platform B, how can it be? So my answer to them is usually that, okay, the OpenVX libraries was developed by the engineers from that company. So they know what they need to do on their hardware. So they wrote the best code using whatever language they have or whatever resources they had to get the squeeze out as much performance as possible for the given node. So when I'm using that, I'm getting that optimized library for me, right? So compared to any open source implementation, which is done by somebody who might not target a given hardware, might not be interested, or might not be supported on a hardware you want to run. So that second point, that having engineers of that company develop APIs for you, is great. And like I said, the acceleration on wide range of hardware and vision hardware architectures gives flexibility to launch on many OSs and hardware. And finally, the graph-based abstraction gives you all those memory, performance, kernel fusion kind of optimizations free of cost. So you're just getting it without having to worry about or think about. So it's already built in the framework. So you're just getting it and you're getting the performance from it. And finally, it's always portable, efficient vision processing is kind of important. And with the Spear right now, where we are at the moment, where everything is a seismic shift towards neural net and computer vision, most applications are getting automated. It's very important that we concentrate on not try to hoard knowledge, right? Not try to make proprietary libraries and trap people into using a given hardware and say that, okay, you can only use this hardware. So that kind of breaks down the progression we are having. So you need to break free, and as a developer, don't get honed into libraries which don't port, or you have to continue on generation with some hardware. So 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 that's the conclusion for this. And a few acknowledgement. I would like to thank Mike Schmidt, Director of Software Engineering at AMD, and AMD's MIVision X team, OpenVX Working Group, Neil, President of the Chronos Group, and the Chronos team for all this. And also thank the uh, guys at your conference for arranging this talk and putting the work to connect with you guys. And thanks very much.
Thank you very much for interesting speech. Oh, you have.
Yeah. Just this is the resource slide. I will provide it to you guys. You can freely distribute. It just has where all the sample implementation, tutorial material, and where the things I talked about is all available on the GitHub or on a blog or something. And a few disclaimers, and that's pretty much it. So if you guys have any questions, we can go right into it, and we can use the time. I guess we are 40 minutes, so we have some time for questions and discussions.
Yes, thank you very much, Kiriti. And now every participant can ask a question in our chat and by hand up in the participant section. But now I have a question about OpenVX. In our university, in Moscow Institute of Physics and Technology, we actively using Raspberry Pi or some mobile devices with Android operating system. So could you tell us about more samples, more successful cases about acceleration of image recognition tasks on these devices?
So, like I said, some of the developers who are developing the application, right? So the application, so they don't really disclose what underneath APIs they're using. So if even people are using OpenVX, it's not like a marketing thing that they say that, okay, this application is using OpenVX. So you need to really go into the application and see what's being used. So with that said, there are a lot of open source projects right now on Raspberry Pi that are doing really great at doing just home security. They're doing object detection, motion detection. They're doing like I saw a project where they did the speed of cars. So you know how you have a school and you have cars going by in front of the school, and you want them to slow down, right? And putting this expensive tech to save people to slow down is really expensive. It costs tens of thousands of dollars. You have a radar, LiDAR, and all that. So people developed a simple computer vision application where it can track the speed of cars by recognizing car at point A to point B and seeing how fast it traveled on the frame with predefined variables that this car is going at this speed, right? All they did is use something like small, like an embedded device like Raspberry Pi. So there are a lot of innovative projects coming up right now, and we have that open source project on AMD's MI Vision X if you're interested. It's called Traffic Vision. So you just connect your camera onto a road and then run a neural net and see what's the speed of the car. I mean, some kind of calibration is required. It's not 100% accurate yet, right? Not as accurate as some LiDAR or something like that, but computer vision is getting there, where you can do some things as complicated as defining speed and stuff on simple Raspberry Pi platforms. And that shouldn't stop students now to try to figure or push the boundaries on things, what they can do now.
Thank you. And now we are waiting for questions. No, we don't have some questions.
Sure, that's okay.
Okay. Please.
In terms of resources, like I said, a lot of open source implementations are available and samples are available. And people sometimes want to try it out, right? So you usually go to a talk and listen to all these claims about computer vision doing this and that, and then you actually see what's being done. And then kind of sometimes it's disappointing that, oh, they told this. So it's always important to go and try it out. So that's why I say, okay, here is an open source sample. Here's the libraries. Go ahead, build it, test it for yourself. Don't believe what, like it's advertised. The difference between advertisement and actual running is you trying it out and seeing how it works. So feel free to go on GitHub and download these samples and trying it yourself.
Well, I have one more question.
Sure.
Are you cooperate or yes? Are you cooperate with some universities when you developing OpenVX library?
So, like I said, the Chronos group is like a consortium, right? Anybody is allowed to join, like companies. So let me quickly share, because we have time. I can actually show you. So can you see my screen?
Yes.
Okay. So this is the Chronos website, and these are all their open standards that they developed so far. You can see NNEF, OpenVX, WebGL. I'm sure you've heard about some of them. SYCL, Spear, OpenCL, OpenGL, OpenXR. So all these standards are from the Chronos group. So what Chronos group is a whole bunch of industry standard people coming together and supporting. So that means that as a university, you can also join the Chronos group as a member, and then have a say at what needs to be done in any of those computing format. I wanted to show all the membership, right? So here's more about Chronos. I wanted to show the list of members. Right, so here it is. So you can see everybody in Silicon, Google, there are members of Chronos. There's a whole bunch of them. There are 160 plus people. So all the companies, so what they do is they come together and define industry standard so that the standards can be portable across OSs, can be portable across their hardware, and the developers get the best out of it. So as university students, you could also actively take part by making sure that your university wants to join as a member, as a university member, and then try to be present in all these standards meeting and see what's happening and just being there, you kind of get the essence of what's happening, and that can help. Like if you're planning to go into the industry, it's good to know what's happening in the industry as students.